Okay, so chaos and fractals. That's maybe not something they teach in a regular high school. If you go to super science high schools, maybe you've heard of these topics. In the 80s, this became a really popular field in math, in mathematics. But more than a century ago, some mathematicians started finding really difficult, complex patterns. Not in nature, but in mathematics, okay? And these patterns are complex because, like, take the top one here. This is the Cantor set. It starts with a line, just one line like this. I'm switching hands. I'm not very good with my left hand. So one simple line, but if you cut out the middle, now you have one line here, a space, and another line. You cut out the middle, and you keep going all the way down. What's the problem here? If you want to measure something about this, like how long the lines are or how many pieces you can get at the end, there's no answer because you never reach a point where you can't make a space in between two lines, okay? Because in theory, this would be infinity, right? We can always cut a line in half or in a third. So it's impossible to measure this kind of thing using normal mathematics, all right? Same thing here. Very simple thing is happening. I take a triangle, and I make a peak on each line of that triangle. And I keep doing this. I could do it 1,000,000 times. I could do it 1,000,000,000 times. I can do it for the rest of my life and never stop, okay? There's no end to that kind of stuff. This is what a fractal is, okay? It means an object, incredibly complex object that has simple rules, okay? Very simple rule. Take out a line, make a fold, whatever, but creates an incredibly complicated pattern, all right? And it ends up looking like a snowflake. Same for this triangle here. You just make triangles in the middle and you go all the way down. And finally, the Mandelbrot set. And here's what's cool about the Mandelbrot set. Just take that in for a minute. How long can a high school student watch this image? Let's see. It's amazing, actually, because we can zoom in as far as we want. It'll never stop, okay? And the pattern inside is always looking like the original pattern, okay? This is the essence of a fractal. Well, what's amazing is that in nature, most of the things you see are also fractal, okay? They're incredibly complex to measure. They don't really have beginnings and ends or any way to measure how long they are or something like that because there's so much structure, you know? Whoops, there's so much structure in the clouds. There's so much structure in the cliffs. There's so many branches and structure in a tree, okay? And so some people figured out in the 90s, or in the 80s actually, if we want to make a mountain for a movie, we can't just put a bunch of triangles together. Because triangles don't look like mountains. This doesn't look like a mountain. But what if we follow very simple rules and we keep doing them, okay? And then you might end up with something like this, okay? Very simple rules generates very complicated pattern, all right? Filmmakers and CGI experts will use these techniques now to create natural-looking objects, all right? So this is what a fractal is. And it was this guy here, Benoit Mandelbrot. If I have a hero in mathematics, it's this guy. I wasn't a good math student in high school, but now I seem to be using it all the time. But partly because he found a way to measure all of these amazing things in nature. And he noticed that, I'm just going to read this because it's very important to realize that clouds are not spheres, they're not circles, okay, or three-dimensional circles. Mountains are not cones, coastlines are not circles, and bark of a tree is not smooth, okay? So nature is very complex, a different level of complexity. So if we want to study nature, we have to embrace and understand complexity. So Mandelbrot had a cool study in the 60s, all right? He asked a simple question. How long is the coast of Britain? Now, if you take geography, you can probably read a textbook that says the coast of Britain is, you know, X kilometers long, or the area of Britain is X square kilometers, or whatever. Mandelbrot said that's not true. It's impossible to measure the coast of Britain because this. If you use a measuring stick, which is like 1 kilometer, you don't get all of the coastline. Then you use a smaller one, you might get more coastline, but not all of the coastline. So now Britain becomes longer. Now we take an even smaller measuring stick, and Britain becomes longer again. So we keep doing this until Britain is the longest thing we've ever seen. But that's not actually true. It is limited. It's a natural thing. Well, actually, the boundary is not natural. It's human, but the island itself is natural. So Mandelbrot's point was, forget about the simple measurement of length. We need a better measure that helps us understand how complex is the coast of Britain. And he found out that it's about as complex as this, 1.25 fractal dimension. That comes up in my talk a lot. And it turns out that this mathematical monster, the Koch snowflake, almost exactly the same fractal dimension, okay? It's interesting stuff here. So math helps us understand natural objects, even very complex ones. But in fact, as I mentioned in the beginning, almost everything we see in nature is fractal in some way or another, in different level of complexity. And here are a bunch of things. So coastlines at the top, galaxies, that's a cool one. What else do we want to look at? Trees and plants, waves and clouds. Sea anemones, that's a good one. Down here, the way bacteria grow, electrical discharges. So many structures in nature are fractal. Now, I have a question for everybody. You see three, they're actually paintings, okay? You see three paintings on the screen. And I want everybody in the audience to put up your hand when I reach the one that you like best. Which one do you like best, okay? Which one makes you happy inside? Let's start on the far left. Anybody? Hands for this one? Okay, how about the middle? Couple people? How about the end? Aha, okay. So this is the least popular. This is probably the most popular. Now, why is that important? A number of years ago, some scientists, this is strange, sometimes scientists like to study art, it turns out. And in this case, the art they're studying is the paintings by Jackson Pollock, famous American painter, all right? And he would paint with this abstract expressionism, they called it. Now physicists call it fractal expressionism, where he would just layer paint on the canvas, throwing it around. But he had a method, okay? And actually, his methods, they started out in the beginning looking like clouds, his paintings. That's down here, fractal dimension of 1.1. And later in his life, well, actually, this is up here, they looked more like trees in a forest, all right? And it changed over time. So physicist Richard Taylor was actually measuring how Jackson Pollock paintings changed over time. It helps them actually, if they find new paintings, and it's dated 1952, it's Jackson Pollock, the art experts can actually check, well, what's the fractal dimension? If it's 1952, it should be around here. So if you see this painting, probably not Jackson Pollock. All right? Anyway, these were three Jackson Pollock paintings at different times in his life. And it turns out that humans, we like certain fractal dimension of Jackson Pollock. Not just Jackson Pollock, but other things, okay? And you can see here, when the scientists played these different, had people looking at different images, all right? From very simple to very complex. People were choosing the ones that were about here, fractal dimension 1.4, something like that, okay, across different experiments. And so you see here, these are eye tracking data, so they're following, using technology, where people are looking, all right? And so if I can go to this next one more time, there's two Pollock paintings here. Who likes this one, blue poles? Can I see your hands? Hands for blue poles? Hands for number 14. Hands. Yeah? One more time, blue poles. Okay, so almost nobody likes blue poles. The fractal dimension of blue poles is 1.85, okay? It's outside of the human range. But number 14 is right there. And so if you are a human, you probably like number 14 better than blue poles. So we have a preference for some level of complexity. It's across culture as well, okay? It's not just Japan or just America or something. It's many different cultures. And so one of my graduate students at the University of California, Davis, was interested, is it also true in monkeys? Okay? So she did a similar experiment. She showed the same images to a group of monkeys, okay, with eye trackers. And she asked, do monkeys care about fractal dimension? And it turns out they do. So monkeys also prefer they also change their preference with fractal dimension. But you can see it's different from humans. They like really complex or really full images, all right? Not the same as humans, but they have a preference. So they notice the difference in fractal dimension of things around them, which is interesting. She thinks we can use this information to make better living conditions for monkeys, okay? Let's make the environment more complex through fractal dimension. Okay, so humans and monkeys are a little bit different in style, but the mechanism is the same. We recognize fractal dimension.